Chapter 15, Part 2. We're going to pick up with tides. So tides are simply that regular fluctuation of the sea surface in response to the gravitational attraction of the moon and sun. In response to that gravitational attraction, the surface of the ocean is going to rise and fall twice a day. So we have 2 high tides and we have 2 low tides. That range can be anywhere from a few centimeters to more than 15 meters. A complete tidal cycle includes what we call a flood tide, where your tide progressively covers a nearshore area until the high tide is reached, followed by an ebb tide in which the tide falls, exposing the nearshore area again. The picture on the lower left shows a low tide. The picture on the lower right shows a high tide in Cook Inlet, Alaska. Now we know that the sun's gravitational pull on the earth is about 46% as strong as that of the moon's, but the moon's closer to the earth. So as you can see in this bottom picture, we have what's known as a tidal bulge. We have one bulge that points toward the moon, the other bulge is on the opposite side of the earth. The Earth's rotation causes that rhythmic rise and fall of the tides twice a day. Now the moon revolves around the Earth every 28 days. So its position with respect to any latitude is going to change slightly each day. The moon moves in its orbit and the Earth rotates on its axis. And it takes the moon about 15 minutes longer each day to return to the same position. We have what's known as a spring tide. Notice the diagram where you see for a spring tide, the moon, the earth, and the sun are aligned. The tides are about 20% higher, so you're going to have the highest of your high tide and the highest of your low tide during a spring tide. A neap tide, on the other hand, notice the moon and the earth are at right angle to the sun. Your tides are about 20% lower, so you're going to have the lowest of your high tide and the lowest of your low tide during those times. 2 other factors that could affect tides is 1, the moon's inclination to the equator. The moon is inclined at about a 5-degree angle to the ecliptic. The ecliptic is that great circle on the celestial sphere that represents the sun's apparent path during the year. And it's called this because the lunar and the solar eclipses can only occur when the moon crosses it. The other factor would be the slope offshore. If you have a gently sloping continental shelf, as we do in the Gulf of Mexico, you're going to have a low tidal range. If you have a steep, irregular shoreline, you're going to have a greater rise and fall in the tides, like in the Bay of Fundy. The tides do impact the shoreline because the area of wave attack constantly shifts onshore and offshore as your tides rise and fall. Now let's look at our waves. So what is a wave? It's an undulation, a disturbance of the surface of a body of water, and it results in that water surface rising and falling. So in coastal areas, your waves are responsible for erosion, sediment transport, and sediment deposition. The crest of your wave, that I've outlined in red, is the top. The trough, as shown in red, is the bottom. The wavelength is this distance between 2 crests, or it could also be between 2 troughs. The wave height is the vertical distance from trough to crest. The celerity, or speed of a wave, is given by the wavelength over the period. So the period is the time for 2 successive wave crests or troughs to pass a given point. Now, as shown in this diagram, you can see that our water molecules move in a circular orbit. There is little or no net movement. The wave base, this dotted line, corresponds to about 1/2 the wavelength, and that is the depth at which the circular orbits cease. Now your waves are going to be caused by your wind blowing over the water, and it's going to generate your waves through friction. The velocity as well as the duration is going to affect your wave heights. Your area that's known as the seas, you can see in this diagram, they're very sharp-crested, irregular waves. As the seas move out from their area of generation, notice you get these nice, smooth, long-crested, rounded waves that we call our swells. Your fetch is a term we use to determine the distance or to represent the distance the wind blows over a continuous surface. Now, our shallow water waves, your wave shape are going to change in the shallow water. We have mentioned already what our wave base is. What we notice is that our wave height is going to increase as your wavelength decreases. A breaker is what you can see here. That is when the wave that's going to steepen as it enters shallow water until the crest plunges forward. So it breaks. A plunging breaker is one in which the wave is going to crash onto the shoreline with steep offshore slopes. A spilling wave is going to be a wave that's going to build up slowly, and the wave crest is going to spill down the wavefront. So you can see in figure A, we're showing a plunging breaker. In figure B, we're showing a spilling breaker. Okay, this ends part 2 of chapter 15.